Hi guys, so in this next part of the unit, we're going to look at how moles relate to chemical reactions. So before we do that, there's just some vocabulary we need to go over. So when you're given a written chemical reaction, the stuff that's in front of the arrow or to the left of the arrow, those are called reactants. And then to the right, we have our products. And when you're reading a chemical reaction or equation, we say the word yields to represent the arrow. So the reactants yield a certain amount of products. So aside from the symbols of the substances that are in the reaction, we also have these numbers. We have coefficients and we have subscripts. So the coefficients are the big numbers that are in front of the substances, and they tell you the number of moles of molecules. So in this reaction, we're producing 2 moles of H2O. That's what that big 2 stands for. And the subscripts, those are the tiny numbers that are in the compound or element, and they tell us the number of atoms in the molecule. Okay, so also, guys, when we write out a chemical reaction, we should also be labeling the phases. So down here, I gave you what the symbols would be. If it was a solid, we would write an S, liquid L, gas G, and then we remember this aqueous abbreviation means that it's dissolved in water. So depending on what's in the reaction, there are ways for us to know what phase of matter we should be labeling everything. So if this chemical reaction, for example, was happening at STP, I already know from the periodic table unit, because we labeled all of our elements and what their phases are at STP, that hydrogen and oxygen are both gases. And then at STP, that's 0 degrees Celsius, we would be making water probably in the liquid phase. Okay. But there are ways to know if we have compounds, what phase of matter those compounds would be in. And we'll get to that a little bit later. Okay, so as far as balancing equations go, we want to think of the law of conservation of matter, which means that matter cannot be created or destroyed. So even though in a chemical reaction, the particles rearrange themselves and they turn into something new, you can't change the amount of stuff you started with. Whatever you start with, you also have to end with. So how do we know that in the lab? If we were to be able to weigh the reactants and get their mass, after they react and turn into products, the mass should be the same. On paper, we would know if matter is conserved by counting number of atoms, and we would want the number of atoms to be the same on both sides, or we'll say equal on both sides. Okay, so here's an example of a chemical equation that's not balanced, and I'll show you how I know that. The first thing you want to do is you want to write the elements that are in the reaction underneath the arrow, and then you want to count up how many atoms are on each side. So I have 2 nitrogens on the left side, and I have 2 hydrogens on the left side, and I have 1 nitrogen on the right side and 3 hydrogens on the right side. So none of these atoms are balanced, and I have to go ahead and add coefficients into this equation to make them balanced. So let's start with nitrogen. Whatever side has a lower amount, you want to go ahead and make that side higher. So on the side where I just have 1 nitrogen, I want to think, okay, well, what would I have to multiply that 1 nitrogen by to make me have 2 nitrogens? Because that's what I need to be the same on both sides. So if I put a 2 here, now I'm multiplying this whole molecule by 2. So what's 2 times 1? 2. So now my nitrogens are equal. When you put a coefficient in front of a substance, that coefficient gets distributed to everything inside of the substance. So I had 3 hydrogens, but what's 2 times 3? Now I have 6. So now if I look, my hydrogens are still not balanced. So I want to go to the side where I have less hydrogen and make that side go up. So over here I have 2, but I want to make that 6 because I want them to be equal. So what do I have to multiply a 2 by? To get 6, I have to multiply it by 3. And that's going to give me 6. So now I have 2 nitrogens on each side. I have 6 hydrogens on each side. This equation is balanced. And wherever you have no coefficients, you could either leave it blank or you could just write a 1. And now my number of atoms are the same on both sides, so I've conserved mass. Okay? These are just some tricks or some examples for balancing equations. And I feel like we kind of already looked at this one, but we'll do this one together. You want to, as always, list your elements underneath the arrow. You want to count how much stuff you have on each side. So on this left side of the arrow, I have 1 of everything. On the right side of the arrow, I have 1 aluminum, I have 3 chlorines, and I have 2 hydrogens. So my hydrogens and my chlorines are not balanced. So right away, guys, you would want to go to the left side and say, okay, well, I need to make my number of H's and Cl's bigger, right? So, okay, let me put a 2 here. That's going to change my number of hydrogens to 2, but it's also going to change my number of chlorines to 2. And I don't want 2 chlorines, I want 3. So a lot of times, and it's okay to like make a mistake here. You could always erase coefficients and try something else. And sometimes that's the only way to do it. It's kind of like a guess and check kind of situation. But usually when there's a 2 and a 3, you need to make both sides equal to 6. So like one of the tricks I would say is to find a least common multiple. And this happens a lot with 2s and 3s. You need to make both elements equal to 6 and instead of trying to make them equal to each other. So if I go ahead and put a 6 here, and I make 6 hydrogens and 6 chlorines, then I need to go to the other side of the reaction and make 6 of those. So if I multiply this by 3, I get 6 hydrogens, so that's good. And if I multiply this by 2, I get 6 chlorines, so that's good. This 2, though, is also affecting aluminum. So if I have 2 aluminums on this side, now I need to go ahead and make 2 aluminums on this side. And everything's balanced. Now, guys, what it's going to say to you when they ask you to balance equations, it's going to say using the smallest whole number coefficients. So when you're trying to find the least common multiple, sometimes you miss the lowest number and you might be thinking like, oh, I need to make both of these equal to 12, right? And you would still get an equation that's balanced. But if the numbers that you put in the coefficient lines, if they're not in their simplest form, you wouldn't get credit for that. So what I want to do before I move on is I want to say, okay, I have a 2, a 6, a 2, and a 3. Can I divide all of those numbers by something to make them simpler? So I can't. There's not a number that can go into all those numbers the same and make them smaller. So I know that was my smallest whole number coefficients. I can move on. All right. Next one. So this kind of looks a little bit scary. Whenever you have polyatomic ions, you're actually allowed to keep them together. So let's write that down. Keep polyatomic together. As long as that polyatomic ion is on both sides of your arrow, you can treat it as if it's one thing, and then that's going to make our counting easier. So in this reaction, I have Fe, I have Cl, I have Ba, and then OH is the hydroxide ion, but that hydroxide ion is on both sides. So I don't need to write the O and the H separately. I can just count it as one thing. All right, I'm going to go through. I'm going to write down how many atoms of each element I have on the left. And guys, your polyatomics, if they're not in parentheses, you just have one of them. If they are in parentheses, you want to use that little number on the outside. On this side, I have one iron again. I have 3 hydroxides. I have 1 barium, and I have 2 chlorines. Right? So we are not balanced here, and we have to get ourselves balanced. So again, right away I'm seeing I have 2s and 3s, and I'm going to have to make these both equal to 6, and that's probably what's going to make me balanced, right? So let's start with the chlorines. If I put a 2 here, 2 times 3 is 6. That gives me 6 chlorines. But that 2 also affects my iron. This is a really important step, guys, is keeping track of the amounts of atoms you have down here every time you put in a coefficient. Because sometimes you forget to keep track down here, and then your equation's balanced and you don't even realize it. So here's chlorine over here. If I put a 3 there, that's going to give me 6 chlorines, but it also affects my number of bariums. Okay, all right, let's do iron. Iron is, I need 2 of them on this side. But that 2 also affects hydroxide. Now I have 6 hydroxides on this side. So if I put a 3 here, that's going to give me 3 bariums and 6 hydroxides. All right, so if I check all my numbers, I'm balanced. 2, 3, 2, 3. I can't simplify that, so I am done. The last type of reaction that's kind of difficult to balance is one like this, where I go through here and I say, okay, I have a C, an H, and an O. Those are my elements. I have 4, 10, and 2. And on this side, I have 1, 2. Now, here's the problem. I have oxygen in this compound and in this compound. And I have to remember to add up all of them to get the total number on this side. So what you want to do here when there's like an element that's in more than one spot is you want to balance that one last. So let's say balance lone element last. And it'll usually work out. So let's do it. First, I want to get my carbons balanced. So if I put a 4 there, that gives me 4 carbons. Now, that gives me 8 oxygens plus this one that I still have over here. So I still don't have an even amount of oxygens, which is why I want to save it for last. If I put a 5 in front of water, that gives me 10 hydrogens. So now my hydrogens are good. Now oxygen again. 4 times 2 is 8. 5 times 1 is 5. So I have 8 plus 5, that's 13. All right, so now here's my issue, guys. 13 is not an even number. So I'll say, okay, what do I need to multiply 2 by to get it to be 13? I need it to multiply it by 6.5. And that gives me 13 oxygens over here. I'm balanced, so I could put a 1 here. Now, if I jump back up to my directions, they say smallest whole number coefficients. So I'm not allowed to leave a 6.5 there as a coefficient. So what you'd want to do then, if you double, anytime you have a decimal like a 0.5, something 0.5, if you double it, that's going to make you come out with a whole number. So if I double that, I get 13. But if I just double one thing in the reaction, then it's not balanced anymore. So I have to double everything else. So this would actually be balanced with a 2, 13, 8, and 10. And you would look and see you can't divide them by any number that would make them all smaller. All right, so those are your balancing. The next thing you're going to have to be able to do is look an equation and say what type of reaction it is. So we have 4 types here that we're going to look at. And I showed you an example using just letters. But how you would know looking at actual substances is very simple. For a synthesis reaction, you're always going to start with two or more things. So here I've started with an A and a B, and then I'm ending with one thing on the right side. Dead giveaway that it's a synthesis reaction. With decomposition, it's the opposite. You're breaking down. So you're starting with one thing, and then you're ending with two or more things. So those reactions are opposite of one another. So single replacement, let's take a look at what's happening here. I have A and B in a compound together, and C kicks B out. So now A winds up bonded to C and B is by itself. That's called a single replacement reaction. So I start with one compound and one element, and I end with a different compound and element. And it's called single replacement because something always ends up single at the end. The thing that gets kicked out of the compound ends up alone. Where in double replacement, so here I have D and B switching places, but they both end up in another compound at the end. So nothing ends up alone. So I start with two compounds and I end with two different compounds. Okay. So guys, I'm gonna number these reactions. 1, 2, 3, 4. And I want you guys in your notes to label whether they're synthesis, decomposition, single replacement, or double replacement. And then I'm going to have the ed puzzle come up and ask you what you numbered or what you labeled each one. Okay. All right, combustion. So guys, these were inorganic reactions labeled up here. If the reaction has carbon in it, it's considered an organic reaction, and we're going to spend a lot of time studying organic chemistry later in the year. For now, you just have to know that combustion is an organic reaction because it has carbon in it. So there's two types of combustion reactions we have to be able to identify. So I'm going to start with methane. This is the gas that comes out of the Bunsen burner, and we know it's combustible, right? So it can be methane or it could be some other fuel. So what the first thing on the reactant side doesn't have to be methane. The second thing though, guys, always has to be oxygen. And in order for complete combustion to occur, the oxygen has to be in excess. We have to have a lot of it available. What do we always make during combustion is we make carbon dioxide and we make water. So this, and this, those are the must-haves to know that something is an organic combustion reaction. It's the first thing that can be anything that's combustible. It doesn't have to be CH4. Incomplete combustion looks a little bit different. So you still have some sort of a fuel. Whoops, that should have been a 2. I mean a 4. You still have like methane gas, and you still have oxygen, but the amount of oxygen you have is limited. So instead of fully combusting and making carbon dioxide in water, you make carbon monoxide and water. So at this point, guys, you would have to be able to identify that it's combustion, complete or incomplete, and maybe balance it. Okay. All right. So this was kind of what I was mentioning earlier too, guys. As far as labeling phases in a chemical reaction, when you have an ionic compound, We learned about the properties of ionic compounds back in the bonding unit, and for the most part, ionic compounds are soluble in water, but we always want to check reference table F to make sure our ionic compounds are soluble, because if they don't dissolve in water, then they're going to stay solid, and we'd want to show that when we're labeling our phases. Okay, so this table F, this is in the Regents reference table, but we would also be giving you this table to take your test in this class, so you don't have to memorize any of this. So basically, if you're in this column, we're labeling you as aqueous. Sorry, guys. I'm leaning on this, and it's this is an exception column. So if you're in this column, that means you stayed solid. You don't dissolve. This is another insoluble column. So if you're in this column, we would name you or label you solid. You don't dissolve in water. And then this is another exception column. So this would be aqueous. All right. So here's how I like to use this chart. When I'm given an ionic compound, I like to look for the second thing in the compound, the nonmetal ion. And you want to look in your main columns first. So this is my main column. This is my other main column. I want you guys to find the Cl ion. So the Cl ion is right here. It's in the soluble column. But before I go ahead and say that NaCl is soluble, I need to check if Na, the thing it's bonded to, is an exception. So is Na one of the exceptions? No. So that means that NaCl is in the soluble column. So I would label it as aqueous. All right, let's try the next one. So I want to do the same thing. I want to look for the second thing, the negative ion in the ionic compound NO3. And I would want to see if I could find NO3 in either one of these columns. I find it here. No exceptions. That means anything with NO3 in it is always soluble. So I would write an AQ. I'm going to write AQ again because I see an NO3. All right. Now AgCl. Chlorine is right here, but Ag is an exception. So typically, when you end with a chlorine, you're soluble, except for when you're bonded to silver, lead, or mercury 1. So this thing would not be soluble. It would be insoluble. So we'd label it S. It would stay in the solid phase. All right. So this is actually it for today, guys. I'll give you one more question using table F, and then we'll do more practice tomorrow.